Hello, Math 201. Welcome to today's lecture, section 4.3, what the derivative tells us. So again, we're just going to continue moving on through these applications of derivatives. You'll notice that I skipped a section. The way the book kind of sets it up is I don't really like the order. So we're going to do section 4.3 first, and then next week we'll do section 4.2. So just know that I'm kind of going out of order here, but okay. So what we did last time, we saw that the derivative helps us find max and mins, both local and global, or absolute. I guess both local and absolute. I think absolute is the term we've used, so I should use the same one. Both local and absolute by finding critical points, right? Critical points are the values C, where f prime of C is 0 or f prime of C is undefined, right? That's what we did last time. We used the derivative to find max and mins of functions, but it turns out the derivative tells us even more. It tells us more because the derivative is the slope of the tangent, right? So if f prime of x tells us the slope of f of x, when the slope is positive, that means the derivative is positive. So the derivative is increasing. And when the slope is negative, that's the same thing as saying the derivative is negative. And so if the slope is positive, that means our function is getting bigger, right? Because the slope is positive. And so a positive derivative tells us our function is increasing or getting bigger. Conversely, or on the other side, is if you have negative slope, if we're going down and to the right, then as we move to the right, our function is actually getting smaller. And so negative slope means decreasing, positive slope means increasing. And so that's actually going to be the definite, that's going to be important fact. So let's define what increasing and decreasing mean. They mean exactly what you think they mean, except for we're going to use a slight kind of, I guess, convention. So when we say increasing, we mean it's getting bigger, strictly bigger. And when we say decreasing, we mean strictly smaller. So for instance, this is increasing on this interval because it's always going up and to the right. This one's decreasing because it's always going down and to the right. So increasing, decreasing, we're going to use the terms non-decreasing and non-increasing if we want to include equality. So non-decreasing means that it's bigger than or equal to as you move to the right. Non-increasing means it's smaller than or less or equal to when you move to the right. So here's an example of a non-decreasing function. So it's increasing on some parts and flat on other parts. So this is non-decreasing. Whereas if I had something like this, that would be non-increasing. Whereas increasing and decreasing, we mean strictly increasing and decreasing. They're not ever going flat. So there's no flatness when we say increasing and decreasing, whereas non-decreasing and non-increasing are going to include the equality. So that's just a convention for this book. Some books do it differently. Some books will use strictly increasing and strictly decreasing, and they would call this increasing and that decreasing, but we're going to use non-decreasing, non-increasing, and then increasing and decreasing. Okay. So when tangent lines have positive slope, the function is increasing. When tangent lines have negative slope, the function is decreasing. And this is actually how we can find out when something's increasing or decreasing. This is theorem 4.7, the test for intervals of increase and decrease. And the basic idea is that if f is a continuous function and differentiable, then if the derivative is 0 on all interior points, then the function is increasing. If the derivative is less than 0 on all interior points, then the function is decreasing. And so this theorem will follow from the mean value theorem, which we'll prove later. But the idea is basically this picture. If your derivative is positive, then the function has to be getting bigger. And if your derivative is negative, then your function is getting smaller. And so that allows us to figure out how to find where it's increasing and decreasing. And so we can use theorem 4.7 to find when a function is increasing or decreasing. And so here's an example. Find the intervals when the following function is increasing or decreasing. Is increasing or decreasing. And so what we do is we're going to find the derivative. So let's find the derivative. The derivative is just the product rule. So it's x. We'll take the derivative of x as just 1. So it's e to the x plus x times the derivative of the x, which is x e to the x. And that's going to just be e to the x times 1 plus x. And if we want to find when this is increasing or decreasing, we want to make make sign chart for f prime of x. So this is the key thing we're going to do. We're going to make a sign chart for f prime of x, and we're going to do this over and over in this lecture. And so what is a sign chart? What you do is you make a number line. Well, first we need to find, so first step, so make sign chart. So step one, find critical points, I guess. Find critical points. So step one is find critical points. So f prime of x equals e to the x 1 plus x. Set that equal to 0 because it's never undefined. And what do we get? We get that, well, e to the x is never 0, but 1 plus x equals 0. So x equals -1 is critical point. And then step two, make number line. Make number line. So we're going to make a number line, and we're going to put in the critical point. So the critical point is x equals -1. And then we're going to test a point over here and test a point over here. So plug in the test point. So let's do 0 for our test point and -2 for our test point. What is f prime of 0? F prime of 0, if you plug in 0, is e to the 0 times 1. It's just e to the 0 times 1, which is 1, which is greater than 0. And so we're going to put a plus sign here. So it's positive there. And then if you plug in -2, f prime of -2 is e to the -2 times 1 minus 2, which is less than 0. So we're going to draw negative signs here. And then the derivative is 0 here. And so it's negative and positive. And so it's increasing. So we'd say that f of x is decreasing on -infinity to -1, not including -1 because it's 0 there. And f of x is increasing on -1 to infinity. And so this is where it's decreasing. It's decreasing here and it's increasing there. So the slope is negative here, then it's 0, then it's positive. And this kind of brings us to what we're going to talk about next, is that if it's decreasing 0 and then increasing, that means that this critical value must be a relative min or a local min, because it's decreasing to it and then increasing away from it. And so that's what we're going to do next. We're going to use the first derivative to classify local extrema. And so here's just kind of a picture of a function with a bunch of local extrema. So the absolute min is here. The absolute max is up here. This is a local extreme, local, local, and local. This is neither, because it's not changing from, it's increasing and then increasing again. So this is not going to be a local max or min. This one is the top of a hill. It goes from increasing to 0 to decreasing. So that's a local max. This one goes from decreasing to 0 to increasing. So it's a local min. This one is a local max because the derivative is undefined and it goes from increasing to decreasing. And then this one is neither because it goes from decreasing to decreasing. And so it's not the top of a hill or the bottom of a valley. And so you'll notice that whenever we have a local max, the derivative changed sign. We went from 0 or positive to negative, from negative to negative if it didn't. And so that gives us a way to test for the derivative. And so this is called the first derivative test. If f prime changes sign from positive to negative, then f is a local max, right? If we go from positive to negative, so increasing to decreasing, we're a local max. If f prime changes from negative to positive, these are all for critical points, by the way, then f has a local min. So from negative to positive, local min. If f prime is positive on both sides or negative on both sides, then f is neither, right? So it's positive, 0, positive. So it's neither. Negative, 0, negative, it's neither. So this is the first derivative test. And so let's put it to practice. So consider the following function. Find the intervals on which f is increasing and those which is decreasing. So that means we're going to make a sign chart. And then we're going to use that sign chart to identify the local extrema. So for part A, we're going to take the derivative. What is the derivative? It would be 12x cubed minus 12x squared plus, or minus 12x plus 12. And so in order to factor this, we'll factor by grouping. So these first two, you can pull out a 12x squared. And what are you left with? You're left with x minus 1. And then if we pull out a minus 12, here you get x minus 1. And then, so this factoring by grouping, you get x minus 1 times 12x squared minus 12 equals 0. And so x equals 1, or 12x squared minus 12 equals 0. And so what does that give us? That gives us x squared equals 1. And so x equals plus or minus 1. So x equals plus or minus 1. So our crit values, are x equals plus or minus 1. And so now make sign chart. Sign chart. So whenever we're doing the first derivative test, you always got to make a sign chart, and you got to get very, very comfortable with this. So let's make a sign chart for the derivative, because we're going to make sign charts for second derivative for f prime of x. So make a sign chart for f prime of x. So the way we do that is put the critical values. So -1, 1. Then we're going to pick some test points. So -2, 0, and 2. And then we're going to check what the derivative is at those. And the nice thing is you don't even have to figure out the value. You just need to figure out whether it's positive or negative. And so if we plug in, so let me record what f prime of x is. So f prime of x is, and I'm going to pull out the 12. It's 12 times x minus 1. And then this would be x squared minus 1. So x squared minus 1. So that's what the derivative is. And so we can plug in values into this. If we plug in -2, so let's plug in f prime of -2, you get 12 times, if you plug in -2, you get -3. And if you plug in -2, you'll get 4 minus 1. And so what is that? That's going to be positive times a negative times a positive, which is negative. So this is less than 0, and so it's negative. So it's going to be negative in that spot. If we plug in 0, f prime of 0, if you plug in 0 into this, you get 12 times 0 minus 1, and then 0 minus 1, which is positive, negative, negative, which is positive. So it's greater than 0. And so we put a plus sign here. And if you plug in 2, I won't even write what the value is. I'll just plug it. I'll just say what it is. It's going to be positive. And then 2 will be positive because 2 minus 1 is positive. And then 4 minus 1 will be positive. And so it's greater than 0. And so it's positive times positive times positive, which equals positive, greater than 0. And so this is going to be positive. Yes. Negative, positive, positive. Yep. For some reason, I feel like I made a mistake, but because it's x minus 1 squared. No, I think that's actually correct because it has a double root. And so this one is not going to be a, yes, okay, this is right. So it's negative, 0, positive, positive. And so it's increasing on this interval and then on this interval. Technically, we could just say this whole thing if we allowed for non-decreasing, and then it's decreasing here. And so that means f of x is decreasing on the interval -infinity to -1. and f of x is increasing, so we'll just put both intervals on -1 to 1 union 1 to infinity, because it's not increasing at 1 because it's technically 0. And so then how do we use this to classify? Well, it's going from negative to 0 to positive, and then it goes 0, positive. And so this is a relative min, but this is neither. So x equals -1 is a local min. X equals 1 is neither. Is neither. Okay, and so this is the local min, and this is neither. And so because of this sign chart. All right, now let's change gears and talk about the second derivative, which is concavity. So the second derivative is the derivative of the first derivative. And so it's how the first derivative is changing. And so on this part right here, the derivative is getting more and more positive. It starts out negative, the slopes start out negative, then go to 0, and then start getting positive. And so this is called concave up. And then here the slopes are positive and then start getting smaller and smaller, go to 0 and become negative. And so this is called concave down. Concave up is a cup, concave down, frown. So I'll write that. Concave up is the cup, so it's a cup. Concave down is a frown, so it's a frown. That's how we remember. Concave up, cup, concave down, frown. And so concavity is defined to be when the derivative is changing or increasing. So when the derivative is increasing, or the slopes are getting more positive, that's concave up. When the slopes are getting more negative, that's concave down. And when it changes concavity, when going from concave up to concave down, that's called an inflection point. And then a simple consequence of how those are defined is that to know when something's concave up or concave down, you really just need to look at the derivative, the second derivative. If the second derivative is positive, then it's concave up. If the second derivative is negative, then it's concave down. If the second derivative changes sign at a point C, so from positive to negative or from negative to positive, then that's an inflection point. And so here's some pictorial examples. So here's concave down, and then it switches. The second derivative is 0, and then it switches to concave up. Here's an example where it's concave up, and then the second derivative is still 0, but it's still concave up, so it's not an inflection point. Here's one where the second derivative does not exist, and then it switches from concave up to concave down, and so that's an inflection point. And here's another one where the second derivative does not exist, but it's still not an inflection point because it's concave down to concave down. Okay, so now we're going to make a sign chart for the second derivative in order to find the inflection points. So make sign chart for f double prime of x. So that's what we're going to do. That's how we're going to find the concavity, is making a sign chart for the second derivative. And so f prime of x, remember the first derivative was 12x cubed minus 12x squared minus 12x plus 12. So then the second derivative is taking the derivative of that, which will be 36x squared minus 24x minus 12. And so we want to make a sign chart for this guy right here. So what we're going to do, set it equal to 0 and solve. If we set this equal to 0, you can divide everything by 12. This gives you 3x squared minus 2x minus 1 equals 0. Then to factor that, I'm trying to think what the easiest way is just do the quadratic formula, honestly. So x equals negative b, 2 plus or minus the square root of b squared, so 4 minus 4ac, so minus 4 times 3 times negative 1, all over 2a, which is 6. So it's 2 plus or minus 4, so square root of 16 all over 6. And so it'd be 6, when it's plus, it'll be 6 over 6. Or when it's minus, it'll be negative 2 over 6. And so 1 or negative 1/3. So those are critical. Those are our possible inflection points. So that's where that's what we're going to make on our sign chart. So now we make the sign chart for it. So this is sign chart for f double prime of x. So let's put those critical values on there. So we have one at negative 1/3, and we have one at 1. The concavity or the second derivative is 0 at those two places. If you plug in a number smaller than negative 1/3, for instance, negative 1, negative 1 there will be positive. So f double prime of negative 1 will equal, will that be negative or positive? Well, that's positive. That will be positive and it'll be bigger than that. And so it's actually bigger than 0. So it'll be positive here. If we plug in 0 into this, 0, 0, negative, and so f double prime of 0 is less than 0, so negative, negative, negative. And if we plug in a positive number here, that one will be much bigger than those two, and so it will be positive. F double prime of 2 is positive, and so it's plus, plus, plus. So that means it's concave up, concave down, concave up. So that means that this is an inflection point, and that's an inflection point because it switches concavity. So x equals negative 1/3 is and 1 are inflection points. And here's that picture of that. So here's the function that looks like this. X equals negative 1/3 is an inflection point because it switches from concave up to concave down, and then it switches from concave down to concave up. X equals negative 1 is an absolute min, which we found. And then 1, remember, is neither because it did not change sign. All right. And then it's so we can use the sign chart to know when this function's increasing, decreasing. It's decreasing from here to here. Then it's increasing from there to there and keeps increasing. And then the concavity is second derivative is positive from there to there. Then the second derivative is negative, and then it's positive. So concave up, concave down, concave down. And so now we can actually use the second derivative test, noticing what did we notice about right here? Well, this is where the critical value was. And we noticed that it was concave up. So when it's concave up at a critical point, then that point is actually going to be a local min. This point, it's switched concavities, even though the second derivative or the first derivative was 0. So it has a horizontal tangent line. So that's why it's not a local max or min, because the concavity switched there. If it was concave up or concave down there, it would have been a local max or min. And so this gives us the second derivative test. The second derivative test tells you that if you have the second derivative being 0, or the first derivative being 0, so you have a horizontal tangent line. If you have concave up, then it's a local min, right? Concave up, local min. If it's concave down like that, it would be a local max. And if the second derivative is 0, then the test is inconclusive. It could be either. And so here's the picture. If you have a horizontal tangent line, so f prime of c is 0, and you're concave up, then you have to be minimum. If you have a horizontal tangent line, so f prime of c is 0, and you're concave down, you have to be a maximum. And if you have it where the second derivative is 0 at that point, then the test is inconclusive. So let's finish up by doing the second derivative test on this guy. We've done it over and over, but what we're going to do is make a sign chart. Or so actually for this one, we don't have to make the second derivative test is nice because you don't have to make a sign chart. So what is f prime of x? We already found it. It was 12x cubed minus 12x squared minus 12x plus 12. The second, and so we know the critical points. We already found the critical points. Crit values are x equals plus or minus 1. F double prime of x, we calculated that was 36x squared minus 24x, and then minus 12. And so the second derivative test says, so second derivative test, what do? second derivative test. So what do? Plug in crit values into f double prime of x. So for x equals 1, let's do that one first. F double prime of x of 1 would be 36 minus 24 minus 12. And so that equals 0. So test is inconclusive, which makes sense because we know that it's neither max or min. So it actually doesn't tell us whether it's a max or a min. So that's why the second derivative test can kind of suck, because it's just inconclusive. And so we don't know whether it's not a max or a min. But for x equals -1, we can do it really quickly. F double prime of -1 is 36, and then it'll be plus 24 minus 12, which is greater than 0. And so because it's concave up, thus it is local min. So that's how we use the second derivative test. The second derivative test is just a quick way to test whether a local max, whether a critical point is a local max or min, although it does have its pitfalls because sometimes the test is inconclusive. And then here's a quick summary of kind of all the different properties we learned about a derivative. If a function is differentiable on an interval, then we say it's a smooth curve. So smooth just means that it's differentiable. So there's no hard points. If the derivative is always strictly greater than 0 on an open interval, then the function is increasing. If it's less than 0, it's decreasing. And then if you allow it to be 0, it's called non-decreasing and non-increasing. If f prime, if the first derivative changes sign from positive to negative or from negative to positive, then it has a local max or local min. If it has a flat horizontal tangent line and it's concave down, it's a local max. If it's flat horizontal tangent line and it's concave up, it's a local min. And if the second derivative is positive, then it's concave up. If the second derivative is negative, it's concave down. And if the second derivative changes sign, then it has an inflection point. So that's kind of a recap of all properties. And that should be able to get you through everything you need for the homework. Yeah, so take care.